Hello everyone, and welcome back to another spatial statistics lecture video. And in this video, I want to pick up where we left off talking about this idea of the first order nearest neighbor analysis, right? And we sort of generated this equation here, which basically for a given distance calculates the proportion of points that have their nearest neighbor within that distance. And then we're going to do that for a number of distances, and we're going to plot that out. And I said that at the end of the last video, I said that that was going to tell us something. Well, in order for it to tell us something, we really need something to compare it to. And what we're going to compare it to, as with most things in statistics, is an expected value. But how do we get the expected value? Well, the expected value also known as complete spatial randomness, right? This is going to come from a Poisson distribution. I don't expect you to be, 100% familiar with the Poisson distribution. Rather, I'm going to just sort of give you the equation that we're going to use to figure out for a given distance, right, for a given R value, what would we expect, right? What probability or what proportion of points would we expect to have their nearest neighbor be within that distance, right? So I'm going to call this one, I'm going to call it GD again, but again, this is, or GR, right? So this is the complete spatial randomness, right? This is assuming that the data was distributed by random chance in space. Okay. So what we're going to have is we're going to have 1 minus e raised to the negative, this symbol called lambda, which I'm going to talk about in a second, pi r squared. Okay. So you're going to see pi r squared, and you're immediately going to think the area of a circle, right? And that makes sense because what we've been describing up to this point, right, has been literally a circle, right? How many points have their nearest neighbor within this radius? That's a circle. That's another way of describing a circle. So our expected value is going to be based on a circle. So that's why this pi r squared is here. This e is here to deal with the fact that this is a Poisson distribution, right? E is part of the Poisson distribution. And then this lambda is something that we haven't seen before, right? This lambda, right? This is something we haven't actually seen before. So what does lambda do? Well, lambda takes into account the two things that you would need to know to be able to get an expected value, right? And you can think about this logically, right? If you wanted to figure out in a given area for a given point how many points would have their nearest neighbor, or what the probability was that that point's nearest neighbor would be within that distance, you would need to know two things, right? You would need to know, one, right, how many points you have, and we've already talked about this. This is the m value that we've seen in previous equations, right? That's one thing, right? If you don't have a lot of points, that's going to affect the probability. The other thing you need to know is how big is the area, right? If your R is really small relative to the total area that these points are distributed over, right, that's going to affect it. So this lambda takes into account both of these, and this lambda is just the density. Right? It is m over a, where a is the area and m is the number of points. Right? So how does this help us? So what this allows us to do is for a given r, right, calculate the observed, I'm going to use g here because that's the name we've given our equation, right? Calculate the observed g and calculate the expected g. Right. Now at this point, right, you could do something if you did this for a large number of g's. You could do something like a chi-square like we did in some previous examples. But let's just talk about for one value. What does it mean? Right? If observed g, let's talk about two scenarios. So let me erase that really quick. Right? Let's talk about two different scenarios. Right? What happens if the observed g is less than the expected g? Right, so this is basically saying we have a lower probability of a point's nearest neighbor being within that range than we do by random chance. What does this mean? Right, this is indicative, or I shouldn't say this is indicative, right? This indicates that at that distance, your points are more dispersed, right? More dispersed than expected by chance. Right, and this makes sense if you think about what we've calculated, right? If you have an expected g, which is telling you the probability that a point is going to, that the distance from one point to its nearest neighbor is going to be less than a value, right? If your observed g is less than that, then that means that there's a lower chance that a point is going to have its nearest neighbor in that distance, which means that more points are going to be farther apart than you would expect, which means that they are more dispersed. So hopefully that makes sense. So that's if it's less. Let's talk about the other scenario, right? What if observed g is more, or greater, I should say, than expected g? All right, well, this is the opposite, right? Now, right, this indicates that at that distance, right, your points are more clustered than expected by chance. Right? So again, hopefully this makes sense. Right? G is less, observed G is less, your points are more dispersed. Observed G is more, your points are more clustered. And obviously the greater that difference, the more extreme that effect. But let's go ahead and do something different. Or let's take this a step further, right? So at the end of the previous video, right, I talked about how we can graph, right? We can graph these things, right? And on the x-axis, we would have our distance, right? This is that r that we talked about. And on the y-axis, we would have that probability that we talked about, right? And so what we can do now is we can graph what we would get expected by random chance. And it's going to look, something like this, where you would expect that at smaller distances, right, there would be a lower chance that your point is going to be within that range. As you increase the distance, right, you're going to increase, you're going to have a huge jump, and then you're going to sort of taper off until you reach a point where they're all within that distance, right? So what we can do is, let me label this, right? This is expected. This is what you would get through that complete spatial randomness. Well, now what we can do here is we can also plot our data. We can plot our observed points, right? And our observed points might do something. Actually, that shouldn't go backwards. That was my bad, right? It might do something like this. Right? So what we're doing here is we're saying, actually, let me draw that, make it a little more extreme. Let's do something like that. Right? So what we're doing here is we're saying that, for these values right here, right? Actually, let's use a different color. Right? For these values right here, right, in this region, right, our observed is greater than our expected, right? Our probability is higher than what we would have expected. So this may indicate clustering. Right, and the same thing up here, right, may indicate clustering. So what about here? Now on the other side, right, we can read the graph and we see this area here. Right, in this area, right, our observed is less than our expected. And what we said before is that this, may indicate that the data is actually more dispersed, or dispersion. Okay. So again, right, we can talk about an individual value being less or more. And we can talk about it graphically. We can see that there may be large swaths where the data is clustered or dispersed or clustered. And again, we're going to have to go in, when we go and talk about this with real examples in R, they'll actually give us some p-values that are going to say whether or not these are actually statistically significant. But again, right, when you see these sort of disparities here, right, that's an indication that you may have clustering if your value is greater than it, or you may have dispersion if your value is chronically less than it. So hopefully that makes sense. I know there's a lot to this video. I would encourage you to go back, rewatch the part you're confused about. But as always, please reach out. Thank you.